Hello everybody, let us start our discussion today. So we have been talking about the phase space and so let me draw a cartoon of the phase space. Remember that phase space is 2n dimensional, n for the coordinates and n conjugate momenta. So let me just represent them by q and p here. And we are talking about a region in phase space, and at some point of time the say there were few particles, and this particle essentially means that each point that I have drawn corresponds to one state of the system. So it may be that all the particles that we are talking about, they're moving under the influence of same potential, and then and individually, so they're not interacting to each other. Then what we are looking at is how their trajectories will be in the phase space. And let me draw their phase space trajectory. So they go to different places, and I am assuming that there are many other points in between, and that corresponds to a new volume in phase space. So there are other points also in between, and these trajectories are one trajectory to the other is infinitesimally separated. So there is no gap between the trajectories. Okay. So this essentially corresponds to a flow in the phase space. Now that we said is kind of analogous to the flow that we see in a streamlined flow in a fluid. So this is analogous to streamlined flow in a fluid. So what I will do is I will take some result that we know for which is true for a fluid and use it directly here. So what we know for a fluid, and this is a fluid where the number of so-called particles are constant. So it just doesn't create or destroy any one of them. This is true for electrodynamics also, where you are talking about particles as charges. And from fluid mechanics we know that there is this statement gives rise to the equation of continuity. What does it tell you? Well, first you define a density which is a function of all coordinates and time. So in case of fluids, all coordinates are all x and time is t, and you say call the density as rho. Then the equation of continuity gives you that del rho del t plus divergence of j equals 0, where j is called the flux or the current in this case, so it's given by v times rho. Okay, v is the velocity of the fluid. So how does this come physically? If I want to remind you, so if I take any infinitesimal volume in the fluid, the only way that the numbers in this volume changes, if this volume is is somewhere in the fluid, is that if some particle goes out from that volume or some particles come in that volume, so the net flux which is given by this, and if the density itself changes, so that is given by this. That's an explicit change in density with time. Okay. So that we know holds for the fluid mechanics. Now, what is density? Density is given by the number of fluid elements, or you can also think about this as the mass density. So it's the mass per unit volume per unit time in a given time. Sorry, mass per unit volume in a given time. Similarly, I can define a phase space density which I call say F. It's given by per unit phase space volume at a given time. So if I have to integrate this density, the total mass in case of fluid is rho times d3x. In case of phase space density, these are the number of trajectories, so that total trajectories will be f times, now d and q. Let me write this as q because that's what we are using for the coordinate in case of with the canonical variables, d and q and d and p. And this may not just be dq1 into dq2 etc. So it should have the proper Jacobian etc. But that is what is my definition of phase space density. And the continuity equation tells us now that will hold, because as we said that this is just like a fluid flow. So the continuity equation will hold, and that will hold because the number of particles are constant in case of a fluid. That gives rise to continuity equation. The mass doesn't change, total mass doesn't change. Here also, I cannot just make a trajectory disappear. The trajectory number at all times should be same. So there is a direct parallel, so I can just use the result from one to the other. And what does this give us? So this gives us del rho, del f del t, sorry, plus divergence, which is a phase space divergence. So I have del qi rho, which is f, times v, which is qi dot, plus del pi f pi dot, and that is equals 0. So that I can write as del f del t plus let us collect the terms where f is constant, and I take the derivatives on the qi dot and pi dot. So I get del qi dot del qi plus del pi dot del pi. And then I am left with the terms where I have del f, del qi dot, and del f del pi dot, and that is equal 0. Now we say that we are only following a trajectory or following trajectories. What do I mean by that? I mean that when I say that f is changing along a trajectory, okay, or along this set of trajectories if you wish. So if I do that, Then I know the Hamilton's equations and pi dot by minus del h del qi. If I do that, then what happens to this term? Well, I have del qi here. Qi dot is del h del pi, so I have just del 2h, and I have del qi in the denominator also. And then I have pi dot is given by this, so I get a minus sign del 2h del pi del qi. Well, these are interchangeable, so this is essentially 0. So this term is 0 if you go along the trajectory. What happened to these terms? These terms can be written now as del f del qi, and qi dot is del h del pi, and the second term is del f del pi, and this is del h. I have the minus sign already here. That you already know, and we defined already as the Poisson bracket of f and h. F comes first because in the first one it is taken derivative with respect to the coordinates, and that makes our expression for f very simple. It just becomes this. That is the continuity equation, corresponds to the phase space, and that has a name called Now, this comes from a very deep fact in physics, in all of mechanics actually, maybe in all of physics. This comes from the fact that the total amount of information that is available to you is constant. You cannot destroy it or create it. I will not get to that discussion here, but if you are interested, please look at the classical mechanics book by Leonard Susskind. It's discussed there in detail. What we will do now is that we will take forward this thing called the Poisson bracket. Okay, so the Poisson bracket is defined this way. So I can define it in between any two quantities A and B, and I have to just mention what are the quantities with respect to which I am taking the derivatives. Okay, so that I write here in short bracket. Most of the times it is not written, but let me just write it for completeness here. And this is defined as del A del qi. Remember that this is respect to all qi's, and I have a summation, the Einstein summation convention is assumed here. So I have a summation over I for this, and then I also have a summation over I for the other term. In the second term, I have P and Q replaced. So A is taken derivative with respect to Pi, and B is taken derivative with respect to Qi. And obviously it doesn't matter in classical mechanics which of these two you write first and which of these two you write second. Now this is this, and you can put various quantities for A and B. Some important results are here. If I have Pi Poisson bracket with Qi, this is 1 if Q, this is Qj, sorry. This is 1 if I equals to j, otherwise it is 0. So this is delta ij. And then I have, if I have Pi with any P or Qi with any Q, These are 0. Not only this, the Poisson bracket also uses a certain or have a certain algebra. So what do I mean by algebra? So I mean that how if you multiply them with a scalar, how what happens if you transpose them, what happens, etc. Or if you add two Poisson brackets, then what happens. So let us write down, list here some algebras of Poisson bracket. And these are the things which you can directly derive from the original definition of Poisson bracket. So I will just list it, and it's your responsibility to derive them. So the relation between the Poisson bracket of A and B and A is that they are just negative of each other. If I multiply one of them, one of the variables A or B with respect to alpha, alpha is a constant which doesn't depend on the canonical variables P or Q's, then alpha just comes out. So it is not commutative and a constant comes out. Then this is also associative. With respect to addition. So A plus B Poisson bracket with C, I can just take the Poisson bracket of A and B separately with C and add them up. And if you have multiplication, that also just like chain rule here. Now I'll write A this side, B C, and then so this is just like normal multiplication and derivative of multiplication, the normal chain rule. You take the Poisson bracket with respect to one and leave the other apart, and then kill the other one with the Poisson bracket and keep B as it is. The reason I have kept A and B in the opposite side is to keep the order of A and B, which is absolutely not necessary here. All these are functions, and the order of functions really doesn't matter. But it turns out that there is a very nice transition from the Poisson brackets to the operator brackets in quantum mechanics, which you call the commutator brackets. And there things does matter because there now they will be operators, so it does matter whether you write A or B which side. So that's why I just have maintained the order. Now there is a certain identity called Jacobi identity. So please check all of these. This also you should check. So this involves three Poisson brackets. And again, this is an identity. It is not something that is completely new. So what do I have? I have Poisson bracket of B and C. I get a function which is a function of P and Q, P's and Q's. And then I take a Poisson bracket of that with A. Now this I do 3 times cyclically, which means that now B comes in place of A, and then C, which is what it was before, and then what I'm left with is A. And then you do it again. Now C shifts to the first place, and I have this. This is 0. Again, please verify that this is 0. There is some usefulness of the Poisson bracket. which has to do with conservation of certain functions along the trajectory. Or so to say, that the conserved quantities along the trajectory follow certain rules. Okay, so before writing that down, I forgot to mention one thing here. So if I have here, there is one more interesting result. If I have the Poisson bracket of A with itself, guess what? This is 0. And that is quite reasonable, because if I write A in place of B here and A in place of B here, both the terms are similar, so there is 0. Okay, so with that, so let us calculate what is dA dt. So A is some function, and I want to ask a question: how does it change along a trajectory? So that's obviously this is del A del t plus del A del qi, that's all qi dot, plus del A del pi, that's all pi dot. So I have a summation over I in the last two terms. And then again, if I write it down along a trajectory, qi dot is given by del h del pi. So this I can write del A del qi and then del h del pi. And this other term, this we have done before, will be minus del h del pi. So you can see that dA dt essentially is del A del t plus the Poisson bracket of A with h. With respect to PQ, of course, which usually we don't always write. So if the A is conserved along the trajectory, then I get this equals 0. So that conservation actually can be tested in terms of Poisson bracket. I have to first check if A is a function of type explicitly, plus I have to check if the Poisson bracket of A with Hamiltonian is 0. If Poisson bracket of A with H is 0, plus A does not depend on time explicitly. Right? Like, for example, consider that energy, that we are dealing with a conservative system. So you have a conservative system. If you have a conservative system, then the Hamiltonian is not a function of time, not an explicit function of time. So which means Now dH dt has to be 0 along the trajectory. And we have just learned that this is del H del T plus Poisson bracket of H with H now. Now this is 0 that comes from here, and this is 0 that we have just seen. So this is a statement for the conservation of a quantity A along the trajectory. So that shows that the Poisson bracket is quite useful. Okay, so now these are the usual discussions on on Poisson brackets. Let me go out of usual a little bit, which you may not have heard in your earlier studies. So remember that in configuration space, this is just to remind you, this you have heard. I can define the distance between 2 points. So say this point is qi, and this is qi plus dqi. So we define the distance between these 2 points as gij dxi or dqi dqj, where gij we call the metric. And we also discussed that the fact that it is there comes from the fact that the Lagrangian, which in this case is a function of qi dot and t, has this form, which is also called bilinear form, where this has like terms like qi dot square. On the other hand, so this means that the existence of metrics makes the configuration space a metric space. So I can ask the question, what is the distance between any 2 points? So I can have a certain geometry in this space. The geometry in this case is called Riemannian geometry. I don't want to go to this more further discussion on Riemannian geometry here. If you are still interested, we can discuss that in the discussion session or even individually. Now let's come to phase space. Phase space. In phase space, our Lagrangian, which was now qi, pi, qi dot, pi dot, and t, is given by pi qi dot minus h, and h is a function of qi and pi, and can be time matched. So this is linear in velocity, even if it's not there, but qi dot or pi dot. Because of that, we could not define a metric here. So you cannot define or you cannot measure the distance between any 2 points, do not have a geometry. Right? Okay, so this was just to remind you a few things. Now, if I look at the structure of the Hamilton's equations, or these are also called canonical equations. Canonical equations of motion. So what are the structures? So this is qi dot is given by del h del pi if you remember the, so I'll write the second other the other equation. If you remember the Newtonian mechanics, you have the form like ddt of a vector equals gradient of a scalar, right? So like the Newton's second law, ddt of p is gradient of minus v. V is a scalar, p is a vector. So I have almost similar thing here. ddt of q is gradient of a scalar which is h. But if I come to the second equation, there is something not so good. I get a minus sign. So I could have, maybe I can construct a vector what vector I construct. So I construct a vector which is like this. So this is not Poisson bracket. So a vector like this. So I have n components here. I have n components here. It's a 2n vector. So let us give it a name. So let's call that capital X. And I put a vector sign also just to remind you that it's a vector. But I cannot write this as, so if this is a vector, the gradient has to be with respect to this, and then I cannot write the right hand side as a gradient with respect to x because I have minus in the second one. So what I do is I define, let's define, so we are fixing things. Our aim is to write the canonical equations in this form, and we'll see that something beautiful will happen once we can do that. So let us define some matrix J which is 0 here, identity matrix here with a minus sign, and then 0 here. But these are n cross n identity matrix. So this is a 2n cross 2n matrix. Okay, so this has the dimensionality of the phase space. So in this direction I have 2n elements, in this direction I have 2n elements, and remember that this is also a 2n vector. Okay, now this has certain properties you can check. So if I do j square, this will come out to be minus 1. So j inverse is minus j. And exercise homework. What is j? Is that a known matrix? matrix that you know from something else, from somewhere else. Okay, so that's, I define J over there. So let us now calculate gradient of H. So now when I write a gradient, so this is again a 2n dimensional gradient, which is defined this way. So del first all Q's and then all P's. Okay. So then this will be nothing but a 2n dimensional vector, which is del H, del Qi, del H, del Pi. Then I calculate this J times gradient of H. So essentially multiply this by J, which is 0 I minus I 0, and here I have n del H del Qi. So these are shorthand notations, as you can see that this is not two elements that this vector have, but two n elements are clubbed into one notation. And what this will be, this if you calculate, this will be a row matrix. The first term is 0, first multiplication is 0, and the second one will give you del H del Pi. And if you do the rest, you will get minus del H del Qi. Now if I write this, now let's check. If I write, I have this x, if I write x dot is equals J gradient H, then let's see what I get. So x is Qi dot Pi dot, its dot is that, and the right hand side is del H del Pi minus del H del Qi. So you now see the canonical equations of motions can be written in that x dot equals gradient of something form, given that, so we have to define a new gradient operator. This is called symplectic gradient. What is this? This is J times grad. So this is my new gradient operator. If I use that new gradient operator, then I can write the canonical equations in this form, that time derivative of the vector equals gradient of a scalar. Okay. Now you may say that why it is important. Why do you want to write it in an old form? The reason is you can go further from here. First of all, you realize that this quantity gives you a vector. So can I now define a dot product between the vectors? Why do I want to define a dot product between the vectors? Well, you see, here this is nothing but a dot product. How do I know what is the distance between 2 points? If I write in vector notation, this is nothing but dx dot dx, where x is that infinitesimal translation vector. So the metric essentially gives you what is the dot product. How do you calculate the dot product? So if I can define a dot product, I can define a metric, and vice versa. If I cannot define a metric, obviously the dot product doesn't exist. So if I could define a dot product now using this vectors, newly defined vectors, x or gradient of that, so then maybe I will be able to define a metric. Okay. So let's see that if I can do it. See, the way I can define a dot product now is the derivative of a scalar gives you the gradient of a scalar gives you a vector, right? So now what I do is I have a scalar b, I take its gradient and I take its symplectic gradient, and then if I have to take, so I do this. So let us calculate this. What will be the symplectic gradient of A and transpose of that? Symplectic gradient of A will be just this with H replaced by A. So if I take a transpose, it becomes a row vector. So this is del H del Qi. Del A del Qi del A del Pi. And J times this we have already calculated here. So I have to replace now H by B. So this is del B del Pi minus del B del Qi. What is that? This multiplied by that minus this multiplied by that, and that looks quite familiar. So this is nothing but our Poisson bracket. So this, now I can define, this is called the symplectic dot product. So Poisson bracket is nothing but a symplectic dot product, and as you may think now that gives you a metric in the phase space. So this defines a metric in the phase space. Which gives rise to a special type of geometry which is called symplectic geometry. Well, we'll not discuss much about it further. Let me just tell you that it has a very nice connection with quantum mechanics also. But let me stop here on our discussion on